my talk is going to be very different from probably any talk here. A little bit more math involved. And the application here is not necessarily related to climate change or heat stress or anything like that. So this is some work that I did with my PhD student Sesha, who is now a postdoc at Truman State University. But what we're going to be talking about is creating a solution to a problem I think that's going to become more and more common when we see climate change and with heat stress and other things that are going on as we energize our globe. So I'm going to give you some background information on disease surveillance. So that's what I'm going to be talking about. And then I'm going to give you guys some background for the method that we developed. I'm going to start at a very low level or a very introductory level, since I know that a lot of you guys are not statisticians and not super familiar with statistics, and that's totally fine. We each have our areas of expertise. So I'll provide some background to hopefully get you through that section. We'll look at a case study related to salmonella cases in Germany. Then I'll talk about some future research direction and then end up with some take-home points for everyone. So you may be wondering why disease outbreaks are important, whether this is something that's a problem here, or maybe it's only in other places. So a couple nights ago, I just jumped on the CDC's websites and was searching for disease outbreak. And so these are the disease outbreaks that are currently being monitored by the CDC, presumably in the United States. It doesn't always say where the locations are. And you can see there's quite a few of them. I'm not sure if this is just within the past year. I see it goes back to October 2015. But there's quite a few of them. And you may notice that pretty much all of them are related to food. There's something about small turtles. I guess that's not food. That you don't know, maybe, I don't know. But most of these look like they're food related. There's different kinds of salmonella. There's E. coli. There's listeria from raw milk, which is really tasty if you haven't tried it. But you've got to be careful for that. And so disease outbreak is a problem not only in developing countries, but it's still a problem here. And the kind of data that we get when we're doing disease surveillance is sort of unique. So this is sort of a preview of the data we're going to be analyzing down the road. And so in Germany, you have these 16 different German states, right? Just like in the United States, we have 50. And most of the time, they aggregate disease measurements over some region. So it could be at the county level, it could be at the state level, and they usually do it over some time period. So maybe a week, maybe a month. For the German data, we have counts in these different German states for each week. So the time period is a week, and every week you get a new set of data related to the number of salmonella cases that were observed in the past week. And so what exactly is a disease outbreak? So I'm just going to cite the World Health Organization, which seems like a pretty reputable source. And a disease outbreak is essentially the occurrence of cases of disease more than what you would expect during the typical time period or over the specific community or geographic area or season that you're looking at. So in its basic sense, it's really just seeing more cases than what you expect. So a lot of times for flu or something like that, there's some sort of baseline number of cases you expect every single year. The question is there an outbreak above and beyond that? And these outbreaks can be very local, right? It could be a city, could be a county, could be countrywide. So we've talked about some of these heat-related stress issues being covering multiple countries and things like that. So the geographic extent, the temporal extent can vary quite a bit. And what exactly is disease surveillance? Essentially, it's trying to focus on establishing patterns of progression. So looking at how this disease, the disease changes over time in terms of what you expect, maybe trying to predict what's going to happen in the future as conditions change. And so you're predicting, you're observing, and then a key detail is you're really trying to minimize the harm, right? So when there's an outbreak, they want to let people know. So for those of you who have children, you may have heard about the measles outbreak last year at Disneyland, or maybe even if you don't have children. There was a measles outbreak because people are not immunizing their kids as frequently as they used to. The perception of disease risk has gone down quite a bit, so people don't do it. And so suddenly there's an outbreak, right? So when there's an outbreak, you want to let people know. If you were in Disneyland during that time period, you're at higher risk. If there is contaminated food products that are floating around. Sometimes they issue recalls, right? So you might hear about this. If you purchase something at Sam's Club or Costco during this time period, there may be increased risk of E. coli or something, so bring it back to the store. The people who are in charge of protecting the public need to be able to let people know that there is an outbreak, that there are usually certain steps that they can take in order to help protect themselves and minimize the risk. And here is why, or an example of why disease outbreak is hard. So this is time series. These are simulated data sets. They're synthetic data. And this black curve here is sort of the baseline risk. It's something that changes with the season, like maybe the flu or something like that. And I simulated some data using the baseline risk. And then also, one of these data sets has an outbreak. Okay, so who wants to identify where the outbreak has occurred in these two time series? And I'm actually looking for interaction here, so if you think you see it, let me know. Does anybody think that they know where the outbreak is occurring, or which one of these? There's only one of them. Top one, bottom one, where did it occur? Okay, so maybe you guys say the bottom. Any idea where, though? 250, so you think about right here, maybe? Okay, so it is actually the bottom, so you got that. But it is not that time period. Okay, but thank you for being vocal here. Got some interaction, that's nice. So this is going to show you exactly when it occurred. So the bottom one, which was in blue, that was when the outbreak occurred. There's no outbreak for the orange period. And so I've overlaid the two time series one on top of each other. And the outbreak occurred between day 150 and day 200. And it's pretty difficult to see that the outbreak has occurred. So this right here is showing the baseline risk when there is no outbreak. And this little blue section right here shows what happened during the outbreak period. You can see we have, this is difficult to see. So I didn't see it when I looked at it. I just created the data, so I knew when the outbreak occurred. And I'm not even sure if this is detectable using the statistical methods I'm going to present. But that just illustrates the problem. So even if you know the truth, sometimes you can't identify it because it's hard. So what's going on here is we actually have disease risk is increasing as we move into the summer period, right? And at the same time as that is happening, we have a greater than anticipated increase in the risk of a disease. And so overall, as the number of counts are expected to increase, we see a slight shift. But the fact that the disease counts are already increasing sort of masks the fact that there was an outbreak, okay? So the question is, can we develop statistical methods to really distinguish the signal from the noise? Because it's just really tough to do this. And there's been increasing interest in looking at prospective disease surveillance. So there's two kinds you can talk about. So one is sort of retrospective or maybe cross-sectional, where you just have a set of data and you're trying to identify where there's more risk for disease than others. The other one is prospective disease surveillance, which we'll be talking about or are talking about. And that's essentially where you're getting data over time. And essentially, as you get data, you're trying to signal whether an outbreak occurs. And so we've had some biological attacks in the United States. We've had various flu outbreaks around the world and in the United States. So I remember when I first started as a professor, that was right when the H1N1 or swine flu hit. So that was a pretty big deal in the United States and at college campuses. There's the Ebola outbreak. And so being able to identify as quickly as possible when a disease outbreak occurs is a pretty big deal. And there's three kinds of outbreaks that the World Health Organization talks about. So one is communicable diseases. These are essentially infections of some sort that are caused by some biological agent. So we've talked a lot about dengue and other diseases I can't pronounce very well, right? So they coming from mosquitoes. But these are something that are communicable. There's biologic agents that are getting into your bloodstream and infecting you. You have disease outbreaks that are caused by chemicals or toxins, right? So we've also talked about some of these heavy metals that can lead to kidney disease. So I guess it's debatable depending on who you talk to, right? Gotta love science. And then there's disease outbreaks that they don't even know what causes it, right? They just know that they're seeing the disease and they have to try to identify the source. So let's talk about statistical methods and at least one approach to solving this problem. So statistical tests. So you're back in introductory statistics now. Okay, so when we're doing statistical tests, this is a formal mechanism for deciding between two competing claims. And usually we call them the Null Hypothesis and then either the alternative or research hypothesis. So this null hypothesis is essentially a hypothesis or belief that nothing is going on. So trying to key in on what we've been talking about. So there's no relationship between dehydration and kidney disease. There's none at all. Okay, so that's one hypothesis, that's one claim. There's no relationship between heavy metals and kidney disease. That might be another null claim. But usually this is nothing is going on. There's nothing interesting to see here. The research hypothesis is typically what we believe is actually true and is usually what we want to show is true. So in this case, it would be that there actually is a relationship between dehydration and kidney disease, or if you are more dehydrated, then you typically suffer from kidney disease at a higher rate. And you have to formally specify this using statistical models and things like that. Let's not worry about those details, okay? So we have these two hypotheses. We want to decide between them. So how are we going to do that? So in statistics, we use something called a test statistic. It's based on some observed data set that you actually have. It usually also is related to our null hypothesis. And it's really a formal number that you use to assess the compatibility of your data with the null hypothesis. So if the null hypothesis is true, is the data I observe consistent with that? Okay, and if so, how consistent or how divergent is it? And once you compute your test statistic, then you're going to have to decide on some sort of decision rule to decide between the two competing claims. So when do you conclude the alternative hypothesis, or when do you fail to reject the null hypothesis? And in statistics, we don't just decide this on a whim. We actually decided to control some sort of error rate, which I'll also not go into in great detail. But basically, we want to make sure we're not wrong too often, right? We actually, and this is what separates, in my opinion, the general branch of mathematics from statisticians. So statisticians want to quantify how certain we actually are. We know there's a chance we're wrong, but can we quantify exactly how likely it is that we're wrong? So we choose this decision rule to control some sort of error rate, and in general, we're going to conclude the research hypothesis when our test statistic is large in some sense. So the process here, so we construct our hypotheses, we calculate a suitable test statistic, and then we decide between our hypotheses using this test statistic based on some decision rule. Okay, and here's another example of why this is tough. And so I simulated a bunch of data sets, and long story short, the orange one here, this orange data set, is when the data, the mean structure has shifted a little bit. So this data set has actually been generated from a different data distribution than the rest of the data. And what we want to be able to do is actually detect that. And if you just looked at that data, you'd have absolutely no hope whatsoever of knowing that that was unusual in some sense. So this doesn't look unusual, does it, from this? Okay, it is unusual. It's not terribly unusual, but it's definitely one of the more unusual observations. And so what I did is I took those data sets, I computed test statistics for each one. The test statistics for the simulated data are shown here in dots. The test statistic for that orange data set is shown here with the orange line. And it's not the most extreme of all the test statistics, but if you compare the observed test statistic with the simulated test statistics, you can definitely see that it's more unusual. So we need statistics to help us make these sorts of decisions. So how do we use these ideas to detect disease outbreaks? Okay, so one of the most popular methods for detecting disease outbreaks is something called the Cumulative Sum Method. And essentially what you're doing is you're sort of compounding the effect of recent observations, trying to assess whether there's been a departure from the expected structure. Another one is the exponentially weighted moving average. I'll talk about that at the end of the talk. And the Q-sum method was actually developed in the context of industrial process control, right? So if you're making widgets, I mean, let's say something simple like soda cans. So we've talked a lot about soda. Okay, you want to make sure that your soda cans are the right dimensions so you can put the right amount of soda inside. And so if your cans are getting too small or too large, you want to be able to detect that quickly so you can shut down your big machine, retool it, and then start it back up and make products of the right size. So this is how the Q-sum method was originally, or how it originally came about. And something called the Poisson Q-sum was developed in 1985 for count data. So since we're counting the number of disease cases, this is a count. And we often model that by a Poisson distribution in statistics. And so you got to change the Q-sum method a bit in order to do the Poisson method, or in order to account for the count data instead. So I have some errors here in my, transferring computers messed it up a little bit. But anyway, okay, so we're looking at a time series of counts over time. So the original mean of this process, or of this process, was 4. And then at time 50, it shifted to 6. And you can see there's a bit of a shift here. And the counts tend to be a little bit larger after time 50. And how does the Q-sum method work? So, as I said, it sort of cumulates or adds together recent observations using a statistic CT, where T denotes the time. So you start off by saying C0 is 0. So at time 0, before we actually observe any data, there's no evidence for a disease outbreak. So we're going to say that C0 is equal to 0. And then at each time step, we take the previous Q-sum statistic, we add to it our current data, so our current response value. We subtract this parameter k that's related to what you expect things to be and what you want to detect. So I don't want to get too much into that detail, but the point here is that we're taking the previous Q-sum statistic, we're adding to it the current data value, and we're comparing that to 0. Okay? And basically, if this is a small number, there's no evidence of a disease outbreak, so we reset the Q-sum statistic at 0. But if there is evidence of a disease outbreak, we let the evidence continue to propagate forward in time. And in general, we signal an outbreak when our Q-sum statistic, CT, is larger than some threshold h, where h is chosen to control some error rate. And historically, in industrial process control, the error rate they used was something called the average run length, which is denoted here by ARL0. And this is the average time between false alarms. And the idea in industrial process control is that we don't want to shut our machine down too often. Because if you do that, then that costs time and money. So we want to make sure that the time between average or between false alarms is pretty big number. Okay? So that's what they did in industrial process control. In general, we actually, in statistics, we control something called the type 1 error rate, which is the probability that if the data is actually from the null distribution, if there's nothing going on, we make the wrong conclusion and say there is. Okay, so that's what we usually control in statistics. And then another thing about this method is it's only for observations recorded at a single location, where a lot of times when we're talking about disease outbreaks, we're looking at geographic regions, right? So this begs the question, is there room for a better approach? So talking with Sesha about things, and based on his research, we said we definitely need to use the spatial relatedness of nearby regions. We need to pool the information in some way. Why would we want to control the average run length? You can't stop a disease outbreak just because you want to. So controlling that doesn't make a lot of sense. Controlling the type 1 error rate is more interested in when nothing is going on rather than when there is an outbreak. And since we're more interested in making sure we detect an outbreak if it's occurring, maybe it would make more sense to control a different error criterion. So we chose something called the false discovery rate, which is controlling the proportion of alarms that are false. So basically, if you had 100 alarms, so you signal that there's an outbreak 100 times, maybe 5% of the time you are wrong. Okay, but it's better to be safe, right, and say there is an outbreak when there's not, than the other way around. Okay, so this was the error criterion that we chose. And the other thing about this is that we're going to be doing lots and lots of hypothesis tests. And it may not be well known, but the more hypothesis tests you do, the more likely it is you're going to make a mistake. And so there's something called multiple comparisons procedures that accounts for this. And when you use the false discovery rate as your error criterion, there's lots of great statistical tools that you can apply to the problem without thinking a whole lot about it. And don't have a lot of time left, so I'm going to skip this. But a lot of this was motivated by actually trying to get the community to use it. So Sesha actually looked at what the CDC, how they evaluated things, and tried to make a method accordingly. So the big picture with what we're going to be doing is that if this was the region of interest, okay, or at least that was what we're focusing on, what we're going to do is we're going to pool the counts, the disease counts from nearby regions, get this sort of aggregate measure over some spatial domain. And then once we do that, then we can apply this Q-sum methodology where we start aggregating the disease counts over time, assuming there's evidence of a disease outbreak. And once we do that, then we can apply these FDR controlling procedures to decide whether to sound the alarm. Okay, so we pool the disease, and then one of the key steps is that you actually have to decide what's unusual and what's not. And so I'm going to gloss over this. but you basically have to simulate data under the assumption that nothing is going on. Because we need to figure out whether an observed test statistic is unusual or not. And as we saw from those previous graphs, you can't just look at the data and say, oh, this is definitely unusual, right? And so we simulate data under the assumption that nothing is going on, and we use that to make our statistical decisions. So how did this affect our results, and how did this improve this? So these foodborne diseases are a big problem, whether it's in the United States or elsewhere. The WHO has launched initiatives to estimate the global burden of foodborne diseases. So this is definitely a hot topic. It's still prevalent in the United States. And for this German data, what we had is we had the weekly disease counts of Salmonella from 2004 through 2014. And then what we did was we used the first 2 years as sort of a baseline period where there were no outbreaks of Salmonella. So we used that to sort of calibrate our testing procedures. And we're looking at this data after the fact, even though we analyzed it prospectively when we did the analysis. And the actual outbreak occurred the first week of November 2011, which is week 110 of our data set. So here's some results for the state of Bavaria. And so you can see the blue line at the top is what you would get if you just apply the regular old Q-sum method, no pooling. The red is what you get when you actually pool nearby regions. So those are the disease counts. This is the Q-sum statistic. And you can see here that at week 410, that pool statistic just shoots through the roof, right? So it seems like there's a lot of evidence that there's an outbreak. And then we use 3 different procedures to decide whether to sound an alarm. And you can see that at week 110 or 410, we start sounding the alarm right away. And at least for the pooled method, so these orange and red lines here, there's a consistent alarm. So it's not like we sound an alarm, oh, never mind, oh, sound an alarm. So there's a nice consistent alarm. So we didn't think that we were making a mistake there. And we see something similar for the second German state. And so what we did, there's a couple things we did. So one is just to look at, well, what happens when we pool versus non-pooling? So when we pooled all the data and we used the most powerful FDR controlling procedure, in every single state, we detected the Salmonella outbreak at the week it occurred. So at week 410, when we got that data, we signaled an alarm and said there is in fact an outbreak. When we didn't pool the data, we still signaled the alarm right away in several of the German states. Some of them there was a bit of a delay, and then in one of them we never sounded the alarm at all, we couldn't detect it. And one of them we sounded 53 weeks later. So there's quite a bit of a delay there. So pooling seems to help. And the other thing we did was just compared it to sort of the state-of-the-art method that people had been using. And once again, we signaled an outbreak at week 410 in every single state. Whereas with the sort of state-of-the-art method, it wasn't detected in, I think, 8 of the regions. And in some of the regions, it was detected right away. In other ones, there was a slight delay. But definitely, the testing procedure that we proposed seemed to have more power in actually detecting the disease outbreak. So future directions. So this method is not perfect by any means. We think it was an improvement on what was available. There's some assumptions that can be challenging to satisfy. So the EWMA method doesn't require as many assumptions, and so we've done some work on extending the same idea to the EWMA method. One of the things that we didn't account for is formally account for correlations. We sort of pooled the nearby regions, but some regions are going to be more similar than others. And so formally taking that correlation structure into account. And then the methodology that we developed actually didn't have any trend or seasonality, so it's kind of a flat baseline. And that's an important thing that we would need to correct for seasonal outbreaks. So what are the take-home thoughts here? Okay, so like I said, very different talk from everybody else. That's fine. So disease outbreaks seem likely to become more common as the globe is energized. So I really liked what Jay said about global energization. There's more energy. There's crazy stuff that's going to happen. So I'm expecting more disease outbreak to occur. We need to detect disease outbreaks as quickly as possible so that public health officials can keep people safe, prepare them, etc. So that's very important. Hopefully you get the take home that it's difficult to distinguish disease outbreak from random variation simply just by looking at the disease counts. You just can't do it, right? You need some sort of formal mechanism for doing so. Good statistical methodology can help to correctly identify disease outbreaks while controlling for some sort of testing error. And then I guess the question in general is, are you using the best tool for the job? So that's all I have. Thank you. Yes, haikus especially.
I wish I could come up with one. You used logically the foodborne outbreaks or something of that type, where you have an acute onset of a condition as compared to patterns of chronic disease changing, for example, CKD.
Sure.
It seems to me likely that they're only different in the time dimension, but how sensitive is your method to having a relatively short time interval between disease onset and its presentation?
So that's a very good question. So I'm not an epidemiologist, and we just worked with what we had, to be honest. That's one of the things I'm hoping to be an outcome of this is, better collaboration. But really it's going to be, I think, being able to detect the disease. And so if you're able to detect the disease, whether it was something that was caused over a long period or a short period, we need to be able to detect the disease. And so, hopefully with some of these awareness things that people are doing with the workers, people get tested more frequently to detect whether they have kidney disease or early onset or something like that. So I don't think that how long it takes to see signs of the disease is as big of an issue as just being able to detect it, period, and getting people in there and finding out that they do in fact have the disease. Does that answer your question?
It does. I was just thinking mortality is a variation on detecting the disease, and that's the way that the CKD was first found in Central America, but it is an acute event.
Sure, yeah. I mean, you could use this on, number of deaths and things like that, just changing over time. Why are people suddenly dying at a higher rate in this population?
I was going to kind of bring up, I think the other tricky thing, and maybe it's not seen as much in infectious disease because maybe more global health initiatives to try to address that, especially in third world countries. But I think also the, getting back to that detection issue, a couple things. One, for instance, in this country, with better healthcare access, we're going to detect more diabetes, but that's maybe not because diabetes is, jumping that much. I mean, sure, rates might be going up just in general because of obesity epidemic, but probably that people didn't know they had diabetes are now getting tested and find out they actually do because they're silent diseases, unlike, salmonella where the person went and got sick. So issues kind of with detection, and then also too maybe issues with reporting because there's Germany, they got one unified global health, so there's just one system to data mine, whereas here in the United States or other places we have a whole plethora and that are not interconnected. And so kind of is there a way that a statistician is able to try to figure out a way of addressing those types of problems?
So it's pretty hard for statisticians to do that. And so we can do things with bad data sets and trying to impute missing values and things like that, figure out how the uncertainty propagates through the system and things like that. But if you have bad data, you have bad data. So like you talked about how maybe it's people are getting tested more, and that's why it seems like there's an outbreak or something like that. In that case, you could do something where you're actually maybe just looking at across a larger region, it's sort of a cross-sectional time kind of thing instead of looking at each time period. And then you're comparing whether there's certain regions which appear to have more of an outbreak than what you would expect compared to other regions. And so we actually, in some research I've been doing with someone from National Jewish Health, we were looking at this respiratory disease. And I mean, people go to National Jewish Health from all over Colorado and surrounding states. So it was seemed like a pretty good data set to test. And based on what we expected, based on population and things like that, we looked at were there more expected cases in some regions than others. And it could just be that healthcare is better now, more people are getting tested. And so if you had just looked at prospective disease surveillance, you might say, oh, wow, there's an outbreak everywhere. But in fact, it's just that more people are getting tested for the disease. But in this case, by looking at everything at the same time period, we could still identify certain subpopulations that appear to be more at risk than others. And so there's definitely some things you can do. And this is why I think it's important to try to collaborate with people who have expertise that you don't have. So when it comes to interpreting data, like I'm not an epidemiologist, I'm not a climate scientist. And so my conclusions may be correct statistically, but make no sense in the field I'm trying to apply them. And so this is where I think collaboration is just so important. So when people are trying to collect data, talking to people who have studied that, and when people are analyzing data, make sure that they're talking to the people who collect the data and know what the data is supposed to be used for.
Well, we're past time, 15 minutes, so we want to thank you, Josh. And Rosemary has just an announcement to make, but thank you, Josh.